in this combined loading problem, we have, once again, a fairly simple looking system, but by the time we're done and treating all the loads, you'll say, wow, this is pretty complex. However, you'll see the straightforward application of the basic models that we've developed to date and the key things that we have to be thinking about, including even the potential limitations of those models. Right, so let's get going. We've got a solid rod that has a collar that is, or a disc that's attached up at the top, and we have some fairly significant loads that have been applied here. But a couple of key things that are going on are that notice that we've got these two vertically oriented 6-kip loads, so a total of 12 kips acting downwards, but they are symmetrically placed. So they're not going to create any sort of bending in one direction or the other. They're nice and straight, are symmetrically placed, so that'll just create a pure axial effect, at least in terms of this overall shaft AB. The 2.5 kip load, though, that's applied, that's lateral, is a whole different ballgame, right? So it's going to create multiple effects that we may have to consider, right? And so certainly for starters, it's being eccentrically placed away from the centroid of the shaft. So it's going to create a twisting effect, but it's also going to create a transverse shear effect, and it's going to create a bending effect that we're going to have to take account of. A whole lot of things going on because of that placement of the 2.5 kip load, right? So we're going to find out what's going on here at this point H. A couple of critical things there. H is located on the surface of the shaft. It is also located directly where the x-axis is located, or above the x-axis, as you see on the image. That matters quite a bit, as we'll see as we go along. All right, so let's switch over to the document camera, and boom, there we go. All right, so here's a synopsis of our situation that we'll take off from. Right, now I simplified the drawing already just to make things a little bit easier. Right there, I took the symmetrically placed axially directed loads and put them at their effective centroid, which happens to coincide with the long axis of the member. So that's going to be a sigma equals P over A kind of business going on there with the total of the 12 kips. Now the 2.5 kips was offset. So I translated that back over into first a torque. So 2.5 kips times the 2 inches gave us the torque that's being applied, right? So right-hand rule going on here. And then it's now being moved over to the centroidal axis. And so now we've just got what's going to turn out to be a bending effect and a shear effect from that 2.5 kips. Our goal is to find sigma max and tau max at point H. We're not going to work through all the numbers. We're going to conceptually set this all up and see what these wrinkles are. And this gets to be pretty complex by the time that we're done. All right, so let's look at a couple of the geometric properties, because we've already identified that we've got axial stresses, bending stresses, shear stresses from bending, and torsional shear stresses going on here. So there's a whole variety of geometric properties that we know that we're going to need, right? And so one of those would be, of course, the basic area. And so that will be pi r squared. And the diameter is 1 inch, so the radius is, of course, 1/2 of an inch. And that would be the net of pi over 4, right? 1 over 2 squared. And so we could, of course, actually divide pi by 4 and have a number if we wanted to. We're going to need the bending moment, inertia, second moment of area, is awkwardly stated. And that one will be pi r to the 4th over 4. And so that will be pi times 0.5 inches to the 4th. Look it up if you need to. What I remembered actually was the polar moment of inertia, which we'll talk about also here. So that's 1 over 2 to the 4th power. That's 1 over 4 squared. That's 1 over 16. So 16 times 4, that would be pi over 64 inches to the fourth. Again, if you don't like that, go ahead and just work out the number if you want. It'd be kind of small. And then there's the polar moment of inertia, which for something like a circle, I know happens to be pi r to the fourth over 2. And since ix and iy are the same here, and the sum of those two would be ip, that's how I reverse engineered what ix would be. I remembered the fundamental aspect of the polar moment of inertia here. So of course that's going to be basically twice as much as this is, so that would be pi r to the fourth. Sorry, r is evaluated as 1/2, so the value would be pi over 32 inches to the fourth. Okay, so there's your geometric properties that you'd have to be able to determine. Right, now let's find the internal resultants at our cross-section, which is not truly at H. H is a point on the cross-section, so that's what we really want down there. Subtle difference, but it actually, technically there is a difference. And then when we go do that, I didn't give myself enough space. That's unfortunate. But there's your 2.5. You've got your axial force and then your torque. Like I said, I didn't give myself enough space. 5 kip inches and 12 kips axial. So it's a fairly straightforward series. Our N is going to be simply 12 kips of compression. Our torque, positive outward normal, and given the way that's all set up, that would be opposite, so 5 kip inches. Our shear force is 2.5 kips. And then our bending moment, we'll have to oppose that. Our M would be then 2.5 times our moment arm, which is 8 inches. So 2.5 kips times our 8 inches, and that will be, I think, 10, won't it? No. See, 2.5 times 8 is 20 kip inches. Right, so there's our internal unknowns, and that tells us the models that we're going to have to be using, right? Because this is going to be a sigma equals n over a. This is going to be, well, that's the torque, or the torque. So that's going to be a tau equals t rho over j, or ip. This one's going to be coming from shear in bending situation. So that's tau equal vq over ib. And of course, this one is associated with sigma equals my over I. Right, so those are the basic models that we're going to have to be working with. That's good to identify. Oh, wow. So this gets to be kind of big and complex. So stresses at H. We've got 4 different things we're going to have to deal with. Right, so I'm going to come back up here where there's a little bit of space, and we're going to show the shaft width, and it is circular, so there's our solid shaft. Here's the longitudinal axis, and our point of interest, H, is right on the surface, and it is located right at that centroid. So let me show you a perspective view, so to speak. There's this long axis, and H is right here. There's your x-axis, there's your y-axis. And H is right. Maybe I should have done that in red. There's your H right here on the surface of the shaft. Okay. That's interesting. So when it comes to the axial, that's pretty easy. Again, we've already figured out what the model is. And let's see, this is in compression. So we're going to have N over A for that compression, right? I'm going to deal with all the normal stresses first. So then we've got the bending. And we are at the neutral axis, so that would mean the bending stress is 0. But let's look at what we've got, be a little precise. We've got compression on one side going to 0, and then we've got tension on the other side, and H is right there. So we actually have, although it's my over I, the I goes to, or the Y goes to 0 on that one from a normal stress standpoint. Right now, let me pull that up a little bit for you. And now so those are normal stresses. Now let's look at the shear stress. Let's do the torsion first. And you have this torque that's applied there. That's trying to wrap this way. And so on the bottom, you're going to have, of course, the reverse direction. That would be your torque going the other way. So we've got then the need for torsional shear stresses going that way, resisting the other way. And so there's your tau out at H that's going to be given to you by T rho over J. That doesn't quite feel right. Why does that not feel right? Trying to twist it this way, we've got to resist it with something going the other way. I guess that's all right. That's going to be opposite of what we got. No, it's not. That's why I was concerned, because I was thinking things ought to build up here, and for some reason I was feeling bad about that. That was your torque, there's your shear, and for resistance, then we've got to have tau equal VQ over IB. Now, that's going to be maximum at the neutral axis. And so that actually isn't a terrible one for a model right there for at point H. This one was C over J because we were at H. The thing is that in that cross section, now let me show you that one. This model of tau equal VQ over B is meant for rectangular cross sections. So it's not quite accurate for a circular cross section to use tau equal VQ over IB over the whole thing, but it is reasonable at the neutral axis, which is where point H is located. So this one would actually be okay. And since I'm playing around with this little circle business, maybe it would be helpful on the torque to help you out too, that here at H, we would be getting shear stresses, right? That would be going around. And remember, they are 0 at the center, and they go increase linearly with rho out to the outer fibers. I know those arrows don't make a whole lot of sense there. Sorry about that. Okay, so these two torques would combine, the two shear stresses would combine to a total big shear stress. And what that means is when we go look at the stress block at H, we're going to get the following kind of situation developing. I told you this simple situation that gets kind of complex here. We have sigma equals N over A And we're at the neutral axis for bending, so therefore all we have is the two normal compressive stresses going on, right? That's just the N over A business. The shear stress on that bottom is acting this way. That's that taw that will equal our TC over J plus our VQ over IB, just at that one specific location. In that model, this part is the approximate part because it is a non-rectangular cross-section, but it might be reasonable at that particular location, right? And once we find one of them, then we know the rest of them, because again, those shear stresses must pinch at the corners, right? So there's your taw values all the way around. NA does not mean not applicable. That means N over A, N divided by A, right? And so that's your stress block you got to work with. Now, if that was the end of it, then we'd be okay. The problem is what they asked for was sigma max and taw max, which is the overall absolute values. So we've got another step that has to be done here, and that is our absolute max has to be found through something like Morse circle, right? And so you got another whole step that you have to work through. Of course, I'm running out of space on the page, but conceptually, let's see what we've got. There's tension, compression, clockwise, counterclockwise. And so we look at that, and this point A has no normal stress, but it has a counterclockwise rotational effect. So that would be point A would be here. And then that one's compression and clockwise, same magnitude. So there and there would be point B, right? So now we got to find the right circle. I don't think that's the right template. So look at this one and see what circle might work out, right? Now I'm confused. I didn't do a good job of scaling this, really, frankly. So let's get the diameter in there, figure out where that origin is at, and then find a circle that reasonably comes close. And there's your Morse circle, and there's your largest compressive stress. We do end up with a tensile, and there's your max one. It's going to be much smaller than the compressive one probably. And then we've got our taw max right here. And that won't be too far off of the taw value that we have over here, but it is going to be bigger. And so we got to keep track of all of that stuff. This has a lot of pieces to it, doesn't it? You betcha. A lot of really good pieces.